Okay, so the one other thing I wanted to talk about in today's class is equilibrium force, and we did this in grade 11 physics. For those of you in first semester, we even did a lab on it. For those of you in second semester, unfortunately, we didn't. Equilibrium force comes from the word equilibrium. And so it's the force that needs to be added to an object to keep it in equilibrium. So if you imagine that you have an object, okay, and one person is putting a force pulling this, oops, be better if I clip the pin. One person is putting a force on an object pulling it this way, and a second person is putting a force on the object pulling it this way. Then the equilibrium force is the force that I or someone else needs to put on the object that will keep it from moving. It's probably going to be back like this. The definition of equilibrium force is that it needs to be equal and opposite to the sum of all the other forces acting on the object. Equal and opposite to the sum of all the other forces acting on the object. In other words, equal and opposite to the resultant. So I could take my F2 and put it up here, line it up so that it's like head to tail, the same length, and then my resultant, blue, would be here, right? This would be my F net or my resultant, and so my equilibrium force would have to be equal and opposite, so it's probably going to need to be a little bit longer. And again, the lab we did was a force board. We had this force board for those of you that weren't in physics first semester, and it had 3 spring scales that we hooked on the edge, and I'll try to remember to bring it out so you can see. Okay, and it was hooked so it wasn't moving, so it was in equilibrium. So we took the reading of these 3 forces, maybe 3 newtons, 4 newtons, and let's say 5 newtons. And then what they had to do was draw vectors to scale of the 3 Newton one, and the 4 Newton one, and the 5 Newton one. And then you had to take and move head to tail your 4 Newton over onto your 3 Newton. They were called A and B. Draw in the resultant and measure it and compare it to the third guy. And it should have been equal and opposite because things weren't moving. So equilibrium force is the force that is equal to but opposite the sum of all the other forces acting on the object. In other words, equal and opposite to the resultant. So I have an example here of what this might look like in grade 12. So you have 2 forces. One is 52 newtons, and it's east 60 degrees north. So it's going to be here. So this is 52 newtons, and this is 60 degrees. So this will be F1x, and this will be F1y. And the second one is west 20 degrees north. So it'll be here. Oops, 40 newtons. This is 20 degrees. So this will be F2x, and this will be F2y. And the question would say, what must be the force exerted on this object to keep this object in equilibrium? In other words, what must be the resultant? So the first step is to find the components. And you know how to do this because that's what we've been doing, right? So the x is going to be the adjacent side, which is going to be the cosine. And maybe by now you can go to F1x is equal to 52 newtons cos of 60. And if you can, please do go to that. Cos of 60 is just 0.5. So this is going to be 26 newtons, and it's going to be east. F1y then will be 52 newtons sine of 60. So F1y will equal 45.03, I think. 45.03 newtons, and that will be north. Okay, so we found our two components for the x. Now let's find our two components for the y. So F2, actually we found our two components for number 1. Let's now find our two components for number 2. So F2x is the adjacent side again. So it's going to be 40 newtons cos of 20. So F2x is going to be 37.59 newtons west. And then the y, this is a 40, is going to be the sine. So F2y, 40 newtons sine of 20. F2y is equal to 13.68 newtons, and that is also going to be north. So once you have these, now so you have two vectors going in the x direction, so you can do some of the forces in the x, and because they're going in opposite, some of the forces in the x, because they're going in opposite directions, you would actually subtract them, and so you would get, what is that, 11? Negative 11.59? I think so. The reason I'm pausing is I think I have a mistake in my problem. The negative means west, so negative 11.59 west. And then you would do the sum of the forces in the y, and they're going the same way, so you would add them. So 58.71 newtons, and that would be north. Okay, so we now have our two components, so we could redraw them. The x is going west, it's going this way, and it's only 11.59 newtons. And the y is going north, and it's significantly bigger, 58.71 newtons. So now we can find our resultant, and our resultant will be here. Square them, add them together, take the square root, and I think mine's probably wrong, because when I subtracted 37 and 26, I got 17, 11.5, so this is going to be rounded, unfortunately, plus 58.71 squared, take the square root, and you get 59.83, I think, so the resultant, or the F net, is equal to 59.843 newtons, square bracket, find our angle, 58.71, and I think the angle is 78.83, maybe? I might be wrong here because I'm worried about my numbers, 33 degrees. Which way was it going? It was going west and then turned and went north. So that's my F net. But the question asked for the equilibriant force. So once you have your F net, the definition of equilibriant force is the force that is equal to, so it must be the 59.843 newtons, but opposite, so opposite west is east. Keep your 78.833 degrees. Opposite north is south. This is my final answer, right? It would be down like this. And that angle would be here. So to be east and then south. Okay, so that's equilibrium force. Not tonight's homework, but tomorrow night's homework will be with some of these. So tonight's homework, page, find the right page. 463, numbers 4, 5, 6, and the hardest part is drawing pictures. And then, of course, you have an assignment to work on. Okay?